EMBL Renewable, and he's going to give us insights into developments and challenges in managing large Cryo-EM facilities. Thank you.
Okay, thank you a lot for this nice introduction. And yeah, I'm here as one of the local EM scientists who is going to manage this ESF platform for Cryo-EM. And we have heard already a lot about the facility itself, so I will like to focus today more on the strategies for challenging samples and how to bring them into EM and improve them for that. First, some short introduction about me. So I started actually in the RNA biochemistry and chemical biology field, then moved over to Holger Stark's lab in Göttingen in 2011. And I will show today part of my work there. And just recently I started here at EMBL, and I will be involved in the managing of the facility at EMBL and as well with the team of scientists at the ESF platform. So we all heard this term resolution revolution, like I think it's an omnipresent term, and indeed it's for me quite impressive to see what's all going on. I will just show a short overview of things which I find important, which we heard already partly about, but which are, especially for me, interesting in terms of the facility. And the first thing I like to mention is actually the faceplate approach, which is actually really powerful for focus and close to focus imaging and bringing small and flexible particles possibly into the high resolution range. And as well as we saw actually yesterday by the talk of Bono, it's as well helpful in the close to focus approach for big particles like the ribosome. And I think it's a really interesting tool which just developed there. This is something which just happened over the last decade, basically, which really changed the field from CCD to direct detectors, and now we have the third generation of direct detectors, and we have a much better DQE compared to all times. And I just want to remember that basically the CCD cameras at the time had a lower DQE than the films, just it was a effect of speed up that one decided to go there. And nowadays we have detectors which are in the low resolution range and high resolution range really good in DQE. Automated data collection is very important. I just show it here in the example of EPU, but there are many other software packages like Cryo-EM, which are good in terms of a facility to improve automatization of processing, because we want to run the facility in a very fast and strategic way. And on top of that, and this is something you saw yesterday as well, we need strategies for basically on-the-fly processing of data, pre-evaluation of the data, and thereby maybe while still recording the data, optimize and change the recording parameters when one sees, okay, somehow defocus change or something like that. But as well, this speeds up the process. And finally, the amount of softwares which are available nowadays, it's just impressive. Recently, there was a change, like now many softwares of those mentioned here are now able to perform GPU processing, and you can just perform over in one day, basically, for some objects on a single GPU workstation, some data processing to a really nice structure. I want to focus today on something else, more on the biochemical optimization of complexes. And complexes need to be optimized already before one goes into EM, and it's a forwards and backwards step actually sometimes between EM and biochemistry to, in the end, get the 3D structure. And yeah, that's just what I want to focus on today. And I do this in case of Cohesin. And I mean, Cohesin is maybe one of those objects which is still underrepresented in the databases, because 25, I just checked yesterday for the keyword ribosome, and 25% of the data in the EMD database there relates to something with ribosome, while many tricky but still interesting objects are not so present yet. And this is something which will change in the next years. And Cohesin is important it forms a tripartite ring-like structure, and it holds sister chromatids together. And basically, here you see the like a drawing of the sister chromatid segregation. The dots are here the cohesin, and there are basically two ways to release the cohesin and thereby allow the segregation of the sister chromatids. And I will focus today on pathway which relates to the prophase pathway for the release of it, which just is for the external or not for the centromeric cohesin. This is a simplification because the biochemistry behind it is kind of complicated, but basically Pds5 and WAPL interact together on cohesin and opens this exit gate, and thereby the DNA can be released. And what we started initially with was not very impressive yet, but still we could see we have this ring-like structure, and we could basically sort for different states of this ring-like and compare it with rotary shadowing results. But it was pretty clear that we cannot work on that by single particle EM nor by any other method. So first we designed, and this is actually a work, here I need to really to mention PIM. So this project was started as a collaboration project between Holger Stark Labs and Jan Michael Peters Lab, and it was really PIM who brought this, who approached us in Göttingen, came with a sample, and how we really started this project. And this was a really nice and as well unexpected development. So the design was to reduce this cold thing here. So basically this is something like 50 nanometer, and we moved something like half of the amino acids to get this bonsai construct. And we could show that actually we have this bonsai SMCs here. And we were able to obtain, by addition of this Pds5 factor, which I mentioned, basically a set of 4 different complexes which we could play with. And the glycerol gradient is just to show that we fractionized our sample, and basically we could get rid of the Pds5 excess which we have, and that we see actually we could check different sections in EM. And now I want to come to another thing which we wanted to optimize, and this relates to the thermal unfolding. So basically, by unfolding, heat unfolding of a protein or a complex, one can optimize the buffer condition with a specific dye which gives some fluorescent signal. And we did this for a big set of buffer composition and pH values, and turned out to find that HEPAS and HEPAS 7.1 was the best condition, and as well the addition of ATP gamma S and magnesium chloride slightly stabilized our condition, so we decided to go for that. This approach was initially just for single proteins or like maximum 3 protein containing complexes. This approach was highly optimized by people from my lab, where they cope for the multi-state steps, which relates to uncooperative unfolding events. So only in case where you have this 2-state, you can only model this 2-state approach when you, and with the melting curve, when you really have this this almost cooperative unfolding, while in many cases, which is far from optimum buffer, actually you see something like this. And previous packages were not able to cope with this strategy. And actually what was found is that many data which is in the database, in the MDD database, are actually far from the optimal pH values, which is guessed from the distribution of PDB complexes, which have a far more broad spectrum, and the results of analyzed structures by this Proteoplex method. Then I want to go to graphics. You heard this already before, and you probably know it, but I want to mention it again. So basically, we have a glycerol gradient where we perform a mild cross-linking with an increasing gradient of this fixative dye. and then we basically run ultracentrifugation, and afterwards we fractionize our sample, and actually we need to quench it and buffer exchange, and then go to EM. And so this is actually really helpful in terms of stabilizing the complexes as well. One can sort out aggregation because we have as well like this fractionation for big particles. So all the aggregates which might still form by inter-complex cross-linking will be sorted away. And in case of Cohesin, we really were able to improve the quality of our particles to get this monodispersed particles, which was not the case before. And moreover, I would always say that it's helpful to run in parallel a non-cross-linked gradient with the same condition, just to see in the gel how it looks like, and then compare basically fractions in EM cross-linked with the fractions here. And thereby we could actually as well see that we have basically a shift of the complex by the addition of Pds5, which is another hint for us to see, okay, we have really this complex. And having these 4 different complexes, we were then able to obtain structures, low-resolution structures, but we were able to compare them. And this is interesting to show because basically this is something like 220 kilodalton. And on top of that, it's still kind of flexible, and we believe that the SA1 and Pds5 addition stabilizes the complexes. So we didn't get a reliable structure for that. By difference mapping, basically, we were then able to define densities within this complex. And on top of that, by rotary shading, we could see that in the full-length complex, as case of Pds5, we actually see an additional density which relates to this Pds5 density, which is shown here. And at the same time, quite some crystal structures were published of Pds5, and they correlate very well to the Pds5 density, which we assign, which has this curved density and interconnects different subunits and thereby possibly stabilize the complex. So that's just the model as it looks like. And to have more data and approach different methods, we were able to obtain, with the help of Franz Herzog and Pascal Yambou, some cross-linking data. I will not go into detail because of time, but basically what we could correlate actually this data, for example, for the N-terminal and C-terminal part of this Pds5 density, which was pretty nice to what we see in the EM density. And the lessons which I want to point on of this talk is basically for many, many objects, some creative strategies need still to be developed to improve the quality of this by depending on the biochemistry of this object. But there are some approaches which can be generalized, which is buffer optimization, graphic stabilization, and subunit addition to make it. Some people add stabilize the complex by antibodies, and still there is a need to develop further straightforward approaches and to bring even those difficult samples into the pipeline for the future and makes them attractive for facilities like us. And that's just the end of my talk. I would like to thank again, especially Pim, who was very important for this project, Jan-Michael Peters and Alexander Schleifer, who did the cold-cold analysis, Jan Kessler, who joined me in Holger's lab, and Franz Herzog and Pascal Yambou for the mass spec data. And I want to thank, of course, having the chance to be here and speak to here, which is just because I just started 3 months ago as scientist here at EMBL. So, yeah.
Thanks, Michel. So there's time for a very short question.
You seem to be using glycerol gradients all the time. Does it work better for you than sucrose gradients?
We tested different gradients, but we used galactose, for example, as well as sucrose. But I think this didn't affect much the result of our graphics approach. We played actually a little bit with the cross-linkers which we used, but and the cross-linker concentration. But I think the galactose or sucrose or glycerol doesn't really play so much a role for us.
Okay, thanks. So let's thank all the speakers of this session.